right, good afternoon. Hello, hello. All right, here we go. We're going to do a few of these. We are, again, still graphing functions using transformations. So this is sort of putting all these things together here today. And then we've got one more thing to do. So you can see this is kind of exhaustive. We are not doing all 12 of these. That's okay. But we are going to do a few. So we want to identify the parent function. And again, these are all the parent graphs that you do need to know and recognize the shape of. So that's the real important thing. So we want to identify the parent function and transformations on the parent function. And then we're going to graph those. Let's do a few of these. What is the parent function here on number 1? Absolute value. So y equals the absolute value of x. And that is our basic function, the most basic. And what shape is it? A V. It's a V. So I want to plot a few of those very basic points, which is that 0, 0, 1, 1, 2, 2, 3, 3. That's good enough. So there is our very basic parent function. And that, then, we are going to transform a little bit. So we have our function f here. And what are the transformations that are happening to our little parent graph here? Eventually, it will go right 1. Yep. And it'll go up 7. What do we have to do first? Flip, yeah. This negative is on the outside of the function, so that is going to affect things vertically, okay? So we have a vertical reflection, which would be over the x-axis, if you want to write it that way, that's the first thing. And then we can shift it up, down, left, and right. So then what are our shifts? We would go right 1, and up 7. Okay. So what I'm going to do then is I'm going to take my parent graph and I'm going to first just flip it vertically. So my positive 1, 1 turns into, if you flip it, where does it go? I got to flip it first. 1, negative 1. So it's going to flip upside down. So here's my vertically reflected graph. Okay. So there it goes, flipped upside down. And now I can take my flipped upside down graph and shift it right 1 and up 7. So I'm going to take my vertex point here. I'm going to go right 1 and up 1, 2, 3, 4, 5, 6, 7. There we are. And then I can put my other few points there to graph it fully. So there is our function f. All right. I don't really want to talk about the rest of this stuff right now, so I don't think that's necessary. Let's look at number 2. Y equals x squared is the parent function. Very good. Y equals x squared. And what shape is that? Parabola, the U shape. What are some points that parabola goes through? 1, 1, and 2, 4. Very good. And then I can use some symmetry to get the other side. So negative 1, 1, and negative 2, positive 4. So there's our parent function. All right, our parent function parabola. All right, and what are the transformations that are happening on this parent function? What does this thing do? Is it inside or outside? It's inside that squaring function, okay? So it's affecting the x, and what does it do? Remember, everything with x is turned upside down. All right, it's timesing by 4. Flip that fraction and multiply. So what is that causing? If we take x values and multiply them by 4, does it stretch or does it shrink? We're stretching it, yeah. So this is a horizontal stretch by a factor of 4. And so if I have I'm going to do it this way. This point right here was 2, 4 originally. It's going to take our x-coordinate, and it's going to multiply our x-coordinate by 4. So what is our new point going to become? 8, 4, yes. 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. There it is. 8, 4 is my new point. And you can see that it really just stretched out horizontally, straight sideways, straight in the x direction. All right? And then this point, which is 1, 1, turns into 4, 1. 1, 2, 3, 4, 1. All right? So it's taking those x-coordinates and just multiplying by 4. And then the same thing happens on the other side. This point, which is negative 1, 1, turns into negative 4, 1. Good. And then our point here, which is at negative 2, 4, is going to stretch way out to negative 8, 4. All right? And so we get this really fat parabola, really wide, stretched out parabola. All right. I love doing point transformations. I think it's so cool. All right. Let's look at number 3. What is our parent function here? Cube. Yeah, it's our cubic function, something to the 3rd power. So that's our cubing function. And what are some points that green goes through? 1, 1, 0, 0. 2, 8. Very good. 2, 8 is the other point there. That's really good to know. 2 to the 3rd power would give me 8. And then it's also got odd symmetry. So negative 1, 1 and negative 2, negative 8. So there's our parent cubic graph. All right. So there's our parent guy. What are the transformations that are happening to our cubic function? Yeah, so this 2 is out in front, so that's going to take our y-coordinates and multiply them by 2. If I take my y-coordinates and multiply them by 2, is that a stretch or is it a compress? Stretch, yes. So this is a vertical stretch by a factor of 2 happens first. And then what do we do after we stretch it? Down 5. Oh, yeah. Yes, this down 5 is on the outside. If it were on the inside, it would look like x minus 5, and then we would have the cube. Yeah? Okay. So this is going down 5. All right. So first we're going to stretch all these points by 2. We're going to take the y-coordinate and multiply them by 2. So what does 1, 1 turn into? 1, 2. There it is. 1, 2. That y-coordinate doubles. This point would become 2, 16. It gets really tall. So this gets stretched a little bit taller. Gets really, really thinned out there, really stretched taller. And now I can shift it down 5. So 0, 0, I'm just going to move down 1, 2, 3, 4, 5. And then it stretches taller. There we go. Okay. All right. Any questions on these so far? All right. Are you getting the hang of transformations? Yeah? You don't, huh? Oh, boy. All right. I think we'll just do 4 and 5. We'll see. All right. Square root function. Very good. So our parent function here, y equals the square root of x. And what shape is the square root? Swoop. Square root swoop. I love that you're using my lingo. All right. So my square root swoop goes to 0, 0. Ooh. 1, 1. 4, 2. Very good. 1, 2, 3, 4, 2. Why 4, 2? What is the square root of 4? 2. That's an easy one. Well, another one we could do would be 9, 3. We could do 9, 3 if we wanted to. Those are nice. All right, so there's my parent function, my square root swoop. Now we have kind of a lot going on here. What is this 3 going to do to our graph? Multiply the y coordinates by 3. It's on the outside of our square root symbol, so it's affecting y values, okay? It's going to straight up multiply those y coordinates by 3. Now, this -1, if you will, is inside the function. What's it going to do to the x-coordinates? It's going to flip it horizontally. That's what it really does. It's actually taking those x-coordinates. It's going to multiply them by -1. So you can think about it that way if you want to. And then last, what is that x minus 2 doing? Yeah, that last is going to go right too. Sometimes I really just like writing it here. We can basically do it in that order. I'm going to do the multiplying to our x-coordinates. So my y-coordinate's getting multiplied by 3, and my x-coordinate is going to become the opposite. It's going to become negative. So let's see. So 1, 1 is going to turn into what? -1, 3. Very good. All right, 0, 0 is still there. What about this point? This point is 4, 2. So the x becomes negative, so that's going to become -4. And then we're 6. We're tripling our y, so 6. 1, 2, 3, 4, 5, 6. Very good. All right, so there's that. Interesting. Okay, so there is our stretched and flipped horizontal reflection there. And then now we can shift, add, subtract things. So now we're going to shift it right 2. So I'm going to take these red dots and move them right 2. I'm going to go right 2 and right 2 for all my dots there. So there's my curve. And this is a big one in terms of transformations, because there's 2 transformations on x, which makes it a little harder. Let's see if we did it right. Square root of negative times x minus 2 inside the radical. Okay, that's pretty good. We can actually check when you do have a nice graph like this, we can actually trace and check our points. When x is 2, we're at 0. When x is 1, we're at 3 perfectly. And when I'm at -2, I'm getting 6, just like I said. So it's pretty cool that we can do that. I think, anyway. I don't want to do that one. Let's do this one, number 6. Let's do number 6. This is an interesting one. What's this parent function? 1 over x, the reciprocal function. Is that what they call it? Reciprocal function? Or? Yeah, is that what they said? Okay. This is kind of a weird way to look at it for our transformation. So I'm going to sort of rewrite it for you so you can see how we might look at it. I can take that -4 off the front, pull it out in front, and then I have 1 over x plus 3. All right, so there's our 1 over x part, and we've got that plus 3 in there. What is the -4 doing to our function? It's times the y. Okay, so -4 times the y values. It is affecting the y values. It's going to flip them vertically and then make them taller, okay, by 4. So it is a vertical stretch by a factor of 4 and also a vertical reflection. So 2 and 1 there, which I kind of like. And then what does the x plus 3 do to our graph? It's going to go left 3. So I just like writing it on there. I think that's pretty clear. We want to do any multiplying before we do any adding or subtracting. So we're going to do the multiplying first. I'm going to graph this. Now, if x is 1, what's the y value? If you plug in a 1. 1 over 1 is 1, so we get 1, 1. 1, 1 is the point. If x is 2, what's the y value? A half. If you plug in a 2 there, it's 1 over 2, right? Okay. So if I plug in a 2, I get a half out. Ooh. It does keep, yes, that's exactly right. We keep getting smaller and smaller, but never touching. What if I plug in a 1/2? What is 1 divided by a half? 2. It is 2. Yeah, so you can check that on a calculator if you wanted to, just to what, it's not this is. Yeah, so 1 divided by a half is 2. All right, so it gets closer and closer up here. So this is this sort of shape like this. It's very crazy. And then the other side also, if x is -1, we would get 1 over -1, which is -1. And we get -1/2 if we plug in a -2. So it's this sort of shape like this. All right, it has a vertical asymptote and has a horizontal asymptote in there. Okay, so that's our reciprocal function. Now we're going to go ahead and transform it. So I have my point here, which is 1, 1, and I'm going to multiply my y-coordinate by -4. So what does this point turn into? 1, -4. So I'm going to go ahead and plot that. 1, 1, 2, 3, -4. So there's my point, 1, -4. All right, and then I also have, so their point, oh my God, -1, 1. Excuse me. Swallowed a fly. That was a fly. It was very small. You couldn't see it. All right. All right. So again, here's my point, -1. Oh, -1. -1 is a better answer there. All right, and then if I multiply my y-coordinate by -4, what are we going to get? -1, +4. So -1, 1, 2, 3, +4. Oh, I went red. Okay. All right, so right there. And so these graphs stretched up and they flipped upside down. So this is our new curve now. It sort of got flipped. All right, flipped like that. Now we need to shift it left 3. So I'm going to take my 2 points that I've got here. And also you should think about this asymptote that's right here, this vertical line in the middle. It's also moving left 3. So I'm going to go 1, 2, 3 to the left. This asymptote moves 1, 2, 3. So we get this vertical line that we're never going to touch. We get really close to, but we don't touch it. And I'm going to move this point also, 1, 2, 3. So there we go, getting very close to the axis there. Getting very close to my vertical line. And that's kind of interesting. Okay. Lots going on in these pictures. I love this stuff. I think it's super cool. Questions on this one? Let's see, square, oh, this is a cube root. I don't care about that. That's another reciprocal function. Absolute value, we're good with that. What's this one, number 11? The staircase one. And, yeah, greatest integer function, staircase. And so it's been shifted left 1 and down 3. Very good. So that's our staircase. I don't want to do those. Just the fact that you know what it looks like is all I really care about, right? So I don't need to draw these out. Good? Yeah? Okay, so here we have what we're going to do today. Consider this your homework. Go, Sasha. All right, so consider this your homework. Class practice is old. I made this up years ago. All right. So, now this is transformations of generic functions, and which this is kind of a big thing. in calculus, these are the pictures that we see a lot in calculus, okay? They're just made up graphs, okay? And what we want to understand is this is how we use function notation, and we can represent our transformations in the same manner, thinking, is it on the inside, is it on the outside of our function, and see what shifts here. We want to shift the function according to the notation and supply the domain and range of the asked things here. What is the domain of my original function here? Good. Perfect. Good job. Domain is, remember, how far left and how far right your function goes. And we have nice solid dots there. So that definitely goes from -4 to 6 on the left to the right there. What is the range of this function? 4 or -4? -4, okay. Bracket -4 and +4, yes. Also at the bracket. And then, so range is how low does it go and how high does it go. So again, our lowest y value is down here at -4, and our highest y value is up here at +4. So there we go. We got range and domain. Okay. So now we're taking this original shape here, which I'm just going to go ahead and just sort of highlight some points here. I just want to make it really clear. So go ahead and highlight those 5 points. So we can make it really clear as we're graphing these. I'm going to graph number 1 here. F of x plus 2 and then plus 1. What does the x plus 2 do to this curve? It goes left 2, and the plus 1 is going to make it go up 1. All right, so there's still transformations. If it's on the inside, it moves in the x direction, left and right. If it's on the outside, it's shifting up or down. Okay, so we're going to take each of these points and go left 2 and up 1. Left 2, up 1. Left 2, up 1. Left 2, up 1. Left 2, up 1. And left 2, up 1. And then connect the dots. And then you kind of domain and range. So there's my shifted function, which I think is kind of cool when you're looking at it. You're like, hey, that's pretty good. All right, what is the domain of this red graph? -6, 4. Very good. And what's the range? -3, 5. Very good. Now, so what's cool is when you start to get really good at this stuff, could I have figured out the domain and range without actually graphing it? Yeah, you can actually just look and say to myself, I would have had to move it left 2, so I would subtract 2 from that and get the -6. All right, so it's kind of interesting. That actually was an SAT question. All right, let's see. I want to do number 2 here. I'm going to do number 2 in blue. F of x plus 1. What's the x plus 1 going to do? Left 1 and then down 2. All right, left 1 and down 2. And again, which one are we shifting? Do we shift the red one or are we shifting the black one? The original f function. Yep, we're shifting the original function. So go back to the black graph, or green, whatever color I use, I guess. And we're going to shift those left 1 and down 2 now. So left 1, down 2. Left 1, down 2. Left 1, down 2. Left 1, down 2. And left 1, down 2. All right, and connect the dots. And there's number... Do you have to find the domain and range of that? Nope. Number 2. Yeah. All right, lost number 3 there. What's number 3 going to do? Yeah, just go up 2. And again, this is shifting the regular function up 2. So we're going to go up 2, the regular function up 2. And each point on our original f function up 2. Great. That's number 3. On the rest of these, you can't really see, but they are nice solid dots everywhere, so assume that they're nice dark solid dots, even though I didn't draw them in.
Well, what if it's discontinuity?
Are any of these discontinuities? No.
But like, since they didn't have a dot, would they be parentheses?
No, that's what I'm telling you. They are, yeah. Assume that they are nice solid dots. Okay? Mm-hmm. All right, your job is to do the rest. And then finish anything else that needs finishing.